one of the key factors is friction loss. The other one is the static head. And in your situation, when you're talking about cooling towers, the static head is an important component because where the cooling tower is positioned relative to the pump suction determines whether you're on suction lift or suction head. You always want the cooling tower to be above the pump, and that gives you the suction head situation that I explained to you was the preferable situation of the two. You can only do the calculation. That calculation is relatively simple. I mean, it's not rocket science. So if you know where the cooling tower is, and you know where the pump is, and you know what the static head situations are, the biggest problem with a cooling tower is more likely to be air entrainment unless they've got good ways of stopping that air entrainment getting into the pump suction line. That, for me, in my experience, is a bigger problem than the actual positioning of the static head. Because NPSH, remember, is assuming that it's all liquid. But when you've got a cooling tower that maybe has got entrained air, you're looking at a mixture of liquid and gas. And that only exacerbates the situation. I mentioned earlier, we're not talking about air being cavitation. It's got nothing to do with air. But if you get air in the fluid, then it makes the likelihood of cavitation worse. If in fact you find on site that the friction losses in the pipework are higher than were calculated, obviously you've got a problem. And this happens a lot. It also happens on the discharge side, doesn't it? People overestimate the head on the discharge side. But those problems you need to find a fix for on the suction side. Now, you can do a number of different things, but it's much more difficult to solve problems on the suction side because you've got a lot less energy to play with. All of the energy is coming from the environment. It's not coming from the end of a motor shaft or something like that. So it's more difficult on the suction side. You really got to play around with the options. What one might be to have a bigger suction pipe leading up to the pump suction and having an eccentric reducer. That way you're reducing the losses in the pipe by having a bigger pipe. And we saw when we looked at tables, we only need to change the pipe diameter by 1 unit, and all of a sudden we got a lot less friction losses. So you can play around with that, but it's only going to give you so much. The key to it really, as I said, is when you're looking at suction conditions, keep the pipe work large, keep it straight, avoid bends, and so on. Those are the sorts of things that solve those problems. You shouldn't be really looking for long suction pipes feeding your pump. That's bad design to me. And I think I mentioned that when we were talking earlier. That the performance of the suction comes from good suction pipework design and good sump design. When it comes to pressure at the pump, the point that's important is what's happening at the suction flange. Okay? And if you've got a gauge somewhere close to the suction flange, whether it's positive or negative may not be an issue. It's a question of how negative it might be. Because remember that when we're talking about NPSH, we're not talking about from atmospheric pressure, we're talking about from absolute zero. So we've got something like 100 kPa to play with. So when you look at the vapor pressure and the liquid and the operating temperature, that's the key component of matching. So you've got to make sure that the pressure at that particular point of the eye is above the vapor pressure of the liquid. And a compound gauge on the suction should tell you that. If it's higher than the vapor pressure, you shouldn't have a problem. That's basically the way it works. You want to have a bit up the sleeve. You want a margin for error. It depends on circumstances and by how much it's negative. I mean, at the end of the day, all you need to do is have a pressure at the flange of the pump that's above the vapor pressure of the liquid. That's all you need. And if it's negative, it's a question of how negative is it. Because remember, you've got that 100 kPa margin between the atmospheric pressure and the pressure at the eye of the impeller. The longer your pipelines are, the worse it gets. The more bends you have, the worse it gets. If you've got air entrainment, the worse it gets. All of these are negatives. And that will be reflected at the pressure that you read at the suction flange. But just because it's below atmospheric doesn't mean to say there's something wrong. It can be below atmospheric and still be okay.